Start the recording. Can you see my screen? Yes, no, please.
Yes, sir.
Okay. Okay, so the slide is inconsequential. Let's get back to what we were doing. So we looked at IP header, the fields in the IP header and their purpose, some of them at least, some of them we said we'll do later. And then we were talking about basically this, if a packet is received at the IP layer, how is it processed? Okay. So it may already have an IP header, that means it's coming from below. Okay, it's packet received from Ethernet, or it may not have an IP header, that means it's a packet that is given by TCP or UDP to IP for further sending. Okay. So we'll see how we put the packet header in both cases. So just as things, so we thought I drew a very dirty looking picture yesterday. It got all messed up and everything, but I think you understood the concept. So I put some couple of nice pictures with all similar concepts in here. I'll put up the slides today. And this is kind of where we were, the flow of packet. The source generates it the application layer. Then it goes to TCP, UDP, TCP puts its own header, IP puts its own header, Ethernet puts its own header, goes out to physical. It'll go through one or more routers, okay? And these routers have only till IP layer because routers don't generate data or consume data. Therefore, they have only till IP layer implementations. There is no need for any higher layers. And then they further send it, finally reaches the destination machine, in which it gets all the way to the application layer again. So recall that in the IP, there was a protocol field. So if TCP sends it, that protocol field will be filled up with TCP's protocol value in the sending machine. And then the destination machine final, when it knows it is the destination, will look at that protocol field, know it is TCP, so give it to the TCP layer. Or is UDP, give it to the UDP layer, or any other protocol that there. So these are not the only protocols that are there out there. Okay. That uses IP. And then this is where we ended. Okay. So request you to kind of try to visualize it again. So when a packet comes, it is going to be checked against the routing table. Okay. And what is checked? The destination. But what is the destination? The destination address in the packet header is the final host destination address. Okay. So if I check that and expect to find a match, okay, to find what is the next stop on the path to the destination, then the routing table should keep one entry for each host. Just one sec. Okay. But then that will explode the routing tables. Just imagine that if all of this, I just gave you that example, if all these packets are coming for all users of BSNL's network, let's say, then think of the BSNL's router. It has to keep one entry for every host that is in every customer of BSNL. Okay, but we'll see that is not needed, but we'll see. Okay, so that is definitely a no. This cannot be done. So what is done by IP is routed by networks. So the routing entries specify the networks, not hosts, which means with respect to what you learned about routing table entries earlier, destination, next hop, cost, okay, the destination field in each routing table entry will be a network address, not a host address. And I'll give you an example, but then just think basically, if IIT Kharagpur gets a chunk of contiguous address, BSNL does not know or does not need to know that this host is in, separately about which host is in CSE, which host is in EE, and anything like that. So BSNL simply will know that this for this entire block of IPs, I need to send it to IIT Kharagpur's router. It does not need to know how IIT Kharagpur has distributed this to the individual hosts, whether it has used all the IPs or not, and so on. Okay. So the destination field that you have seen so far in the routing table entry will be a network address, and this is what is called that IP routes by network. IP does not route by host, which means I don't match the host address with the host, I match it with the network. And we know the network is basically given by an IP address plus a mask or the slash part, basically, whichever way you specified the mask. The slash part basically specifies the mask one. Both of them identify which parts of the entire IP address that I'm giving you is the network part, which part is the host part. Now, if I do this, so think about this again thing out there, even if I do routing by network, okay? So, okay, let's look at one example. This is simple, okay? So this is an example. So I have these networks here and the networks here. And there are these 4 routers. This is this network's router. So this is what I called kind of a gateway. So this is just another name. Normally, when it's an edge network where actual sources and destinations are connected, the router is usually called a gateway. Okay, but again, that's just a nomenclature. Both are basically performing routing actions. Okay, so this is the link. If you see, this is in the network 10.2.2.0/24, and this is what I discussed. That this link and this link, okay, they must have an IP address from this network. So they got 2.2.1 and 2.2. Same here, the network is 330/24, and ID 3.3.2 and 3.3.1, and same for here. So this router, for example, has 3 interfaces, 3 cables going out from it, 3 network cards basically, and each of them are on a different network. This one is on this network, this one is on this network, this one is on this network. And this interface, each of those interface has an IP in that network through which it's connecting this, as we have discussed earlier. Now, if I look at the routing table of this the middle one, the router A, okay. So it says destination field is 10.11.00/16, which is this network, okay. The next hop is 10.1.1.2. So this is an IP address. So this is basically one machine, one router, one gateway, one interface to send it to this. Okay. And this one you will see in different form in different routing tables, but basically saying this is which interface, the name of an interface. Internally, you keep track of that this interface basically means here. So kind of think that in order to reach this 10.1.1.2, which is the interface that I should use? If I have 3 cards, through which card is 10.1.1.2 reached? Okay. So this is just a name for the interface that is going to be used. Cost field will be there. I've not just shown it here, basically. Okay. Similarly, 10.12.0.0/16 will be used through 10.2.2.2 and 13.this one to this router, whose ID is 3.3.3.2. Okay. So important is this destination field will be this. So this is /16 network, just suppose. So there can be so many machines out there. But then this router basically does not need to know where these machines individual things are, because all of them must pass through router C anyway. So just have one entry which says what is the network out there. Okay. And this is also the idea for the next thing. So now, if I have, so I have got routing by network. So my destination addresses are networks. But then think about this BSNL's router. Okay. So if the networks were, if I've subnetted, let's say, one CS network, one electrical network, one mechanical network, okay, so each subnet. So CS subnet, electrical subnet, mechanical subnet, and so on. So by itself, routing by network will still need one entry per subnet, because all I have said is instead of keeping track of each host, keep track of each network. And remember, a subnet is also a network. Okay, but it's still very large. And going with the same example, you realize that BSNL does not need to know that IIT Kharagpur has broken things up into CS network, electrical network, mechanical network, and so on. It can just pass all those packets to IIT's router, and then IIT router will decide oh, this packet is for CS network, this packet is for electrical, this for that subnet, and so on. Okay. But this is possible because of a technique which is broadly called CIDR, classless interdomain routing. So it is not just routing, it is actually a method which does both basically. So this gets possible. I'll show you an example next slides, because we allocate IPs in contiguous blocks. Okay, that allows us to do something nice. So IPs in contiguous blocks using classless address. So CIDR says allocate IPs in contiguous blocks and then combine contiguous networks into a larger network. So it's larger network or what are called supernets for this routing purpose. Just wait with me for 1 minute. I'll show you an example. So this contiguous block allocations with classless saves IP space as we have seen and reduce the routing table size. We'll just see an example. So this is what is called supernetting, also called route aggregation. I aggregate the routes to get a bigger route kind of. CIDR and supernetting are used interchangeably. CIDR is probably the more formal term. And remember, it is not just routing, it's a way of allocating the IP address along with doing something with routing, which I'm going to show. So let's go through this example and kind of try to understand it. Suppose I'm a company X and I need 1000 IP addresses, okay? And I apply to my ISP Y. Okay, we'll see even this gets tricky later on, but just now suppose it is. And ISP Y allocates basically this thing /22. So /22 means what? 22 bits network, 10 bits host. So 10 bit host is 2 to the power 10 machine, that is 1024 addresses. So enough IP address that X needs. Okay. Now internally, X now subnets this into 8 subnets with 128 addresses each. Okay. So what did it have? Okay. Remember, it has 22 bits here, and then it had 10 bits, so 1000000000. These are the host part. I want 8 subnets. I want to break it up into 8, so I kind of further take these 3 bits out. Okay, because 128 is 2 to the power 7. I have 1, 2, 3, 4, 5, 6, 7. So this part is now my host part in each subnet. Okay, and this is my subnet part. So this is the one I will vary from 000, 001, 010, so on and so forth, 111 to get me all the subnet addresses. But now there are 25 bits, 22 plus 3, so my subnets will be /25. I have also put up a more detailed example of subnetting earlier in the slides. When I upload it, you can read it. But I think you know the concept. So if I do this, this becomes 128.0. First one. Second one is what? This is where the next octet starts, remember. Okay. So this 00, then 1. So that means 128 dot, remaining bits are all 0. Okay. Dot 128.25. Then this has come here. This is 129. Okay. It's not 120. Yeah, 129, because this is the last bit of the previous octet. Okay. So just work this out. So these are my subnets that I get. 129.0, 129, 128. This is a pattern to it. This is. So got 8 subnets, and they are contiguous. Okay, because they all got basically derived from this 192/22. So you see, ISP-Y's router does not need to know that X has divided this into 8 subnets and all, because irrespective of which subnet the message is for, okay, the packet is for, Y will have to send it to X's router. Then X can further decide that each of them has, this goes to subnet 1, this goes to subnet 3, and so on. So, router of X, the company X, will have 8 entries, 1 for each subnet. Okay. So now remember this picture. You have these subnets. Okay. Each of them has a gateway, and here is your RX. Okay, and each of these gateways are connected to RX. So this is the gateway of subnet 1, this is the gateway of subnet 2, this is the gateway of subnet 3. And again, gateway is a term for edge networks. It's basically a routing, doing routing. Okay. So Rx will have entries like, okay. So if I look at my subnets, what was the subnet? 192.60.128. Okay. I have 192.60. So this is my RXS router. Dot 128.0/25. So I specified the mask by slash notation. This will say this is the router. So whatever the IP address of this. Then 192.60.128.128/25, the gateway of G2. Okay, the subnet 2. And so on and so forth up to 190.60. I think it was 131. Yeah. 131. 120.31.0. Sorry, 128/25. This will be the G8. Okay, so this is the company access router. What about company Y's router? It does not need to know this division. So we'll aggregate all these routes, form a larger supernet, basically the net that was given to X. Just one second. Just one second. Okay. 192.60.128.0/22. It will have RX's IP address. Okay. Without this supernetting, okay, you had to have one entry at RY's router also. Even if I just do routing by network. Routing by network just says for each network have an entry instead of each host. Now I have 8 networks. A subnet, remember, is a network, full-fledged network also. I would have had 8 networks. But because they were contiguous, I could do this only because they were contiguous. Okay, I could just supernet them into something /22 and then say everything that comes from anything here, send it to RX. Okay. So suppose a packet comes for 192.60.128.37, which is basically in this network. Okay, or let's put 137. So which is basically in subnet 2. Okay. Now what will happen is this is 22. So I will do a subnet masking of 192.60.128.137. The 22 bits I will take out from here and I will match it here in RY. RY will find that these 22 bits are the same. Note that the 22 bits are the same for each of those subnets, right? Because remember this was the 22 bits. This is same for each of these subnets. This has not changed. So anything coming for anything here, this 22 bits will be same. If I subnet mask it with 22 bits. Sorry, bitwise and with 22 bits. So this will always find anything in here matching here, send it to RX. Now RX will match it with this. This one will match with only this one, won't match with this or this because these are matching 25 bits now. So this will be sent to G2. Are you with me? Yes, no, please.
Yes, sir.
So this is what is called supernetting or route aggregation. Keeps higher layer routing tables small because they can aggregate routes to have one entry for maybe 10 networks that are contiguous. Okay. It's possible, remember, only due to contiguous allocation. So CIDR is a technique both encompassing contiguous allocation and this routing table aggregation. Okay. And this is just talking about what all I said basically. So it's possible because of two things, contiguous and classless. So this 1024 block that I gave, if you look at this, this will be seen that this is basically 4 contiguous class C blocks. But I don't talk in terms of that I've given you 4 class C blocks. I say I've given you this side network /22. Okay. I look at it as classless, use subnet mask to distinguish, and then do this process. Okay, so we have seen what a routing table entry in IP network will look like. Okay, so this is just what I have already drawn, so you can look it up later. All right, so here is kind of a summary. The routing table will contain networks in prefix form or explicit net mask form. Okay, not net mask form. Maybe sometimes some host. Host is nothing but a 32-bit prefix. Okay, so everything must match exactly. I'll show you an example. And the next hop address for each packet, plus some other information like cost and all. But right now, for our purpose, let's assume there is only one route to the destination. So I just want to know what is the next hop for this particular destination address. Cost comes into picture in the routing protocol itself for updating the routes, and in forwarding in some cases where you have multiple routes and then you want to choose one with the lower cost and so on and so forth. But right now, let us ignore cost for some time. Okay? And this is the other thing that you need to know. Routers always do what is called the standard term that you should remember, longest prefix match. Okay, so you're expected to know when I give you a routing table and say what will it match with and what will be the next hop and all, we'll do a longest prefix match. What is longest prefix match? It says if more than one entry matches, take the longest match, the one with the longest prefix. Here's an example. Suppose there are two entries, 192.65.00/16 and 65.128.0/24. Okay. If the address is 128.4, it will match both this and this. Okay, because the top 16 bits are 192.65, so it will match this. Top 24 bits are 192.65.128, so it will match this. But for the purpose of deciding the next hop for the packet coming with this destination address, I will choose this because this has matched the longer prefix among the other. So this is what is called a longest prefix match. Okay. And usually you will also have a routing cache. So it's not that always you do this matching and all, because remember this searching through a table. And this is another very interesting area of research, both hardware and software wise. Okay. In speeding up routing table searches. There are books on that. There's nice algorithms and so on. But that's a digression. Let us not go in there. Okay. But you don't want to search all the time. So sometimes I will just remember for some time in a cache that if this, then the next hop is whatever the next hop for this one. So I will look up the cache. If it is there, I will not do this routing table entry matches. So usually there is a routing cache. But if it is not there, okay. So we'll get back to packet forwarding, but this is kind of the thing. So I get an IP packet. Let's get kind of summarized. I get an IP packet. Suppose I received it from Ethernet. Okay. What will I do? I will first decrement the TTL. If the TTL becomes 0, I'll drop it because it has kind of put its on maximum path that it can travel. Okay. If not, I'll check the checksum to see if the header is proper or not. Remember, the checksum is for IP only on the header. If the checksum is proper, okay, then I look at the other fields. Otherwise, I drop the packet. IP does not try to do any error directed correction or something. No error control, nothing. It's a best effort service, unreliable best effort service. So if checksum does not match, I drop the packet. Okay. Now I look at the destination address. Is it for me? Yes. I look at the protocol field, see which protocol's data it is carrying, give it to the higher layer protocol software. If not, I match the destination address against each entry in my routing table. What is the match? I take the IP address, the destination IP address. For each entry, I bitwise AND it with the subnet mask to get out the network part, match it with the corresponding network address in the destination address. If it matches, that means it has matched that routing entry. I do this for each entry. It can match more than one. Finally, I select the one that has matched the longest. The largest prefix it has matched. Then I look at the next hop field of that. That is the next stop to which I should send that. And if I don't find a routing table entry, it matches nothing. That means I don't know what to do with it. I just drop it. Is this picture somewhat clear in your head? Because we'll see there are more details now. We'll go into further details. But is the picture clear? Very important to understand. It's very simple. You should always think that a packet flowing, received, what happens at each layer? How is the header process? If it is coming from below, how is the header process? What steps are taken? If it's coming from up, down to some TCP to IP, IP to Ethernet, okay? You say, how do I add the header? How do I get the values of the different fields in the header? You do that once for one source, two routers, one destination, you understood IP perfectly. Is it clear? Can I proceed?
Yes, sir.
Oh, good. Okay, so I just thought I will show you a simple routing table. This is from a PC. Okay. The router's routing tables will look much more complex, right? This is actually from a PC whose address is 10.124.52.149. Okay. So think of, if a packet comes from 10.124.52.149, which are the ones it will match? It will match this one definitely, okay? Because if I bitwise AND with 0000, it's always 0000, okay? So it'll match this one. It'll also match this one because top three bits are same, 258, 252. This is the network part, so it'll match this one. This is what I was saying as the host route. Okay. Note that it's all bits are one. So everything is network part. What does that mean? It basically means it's a host address. You don't have many manipulation, space for manipulation at the end zeros. Everything must match. So it'll match this also. But then, so it matches three entries. You can verify it don't match any of the other ones. Okay. You can obviously see this one it won't match because this says you should match every bit. But then when I match every bit, this 255 and 149 will be different. Okay. So only these three matches. What is the longest prefix that has matched? This is the one. Okay. And then this on link is a special word for Windows. This terminologies will vary across machines a lot. Okay. But basically what this is saying is this is the here. Whatever you have to do it in this machine. So the interface is specified as this. In Linux and all, you will see sometimes an Ether 0 or something like that G thing that I said. It's a gigabit Ethernet 1 basically. Okay, so this will come in different form, but basically this is telling me that this is the one. On link is telling me this is the end machine. Whatever has to be done on this machine. No further need to route. Okay. Whereas if a packet comes for 10.124.52.7, let's say, that is the destination IP. Okay. So it matches, this always matches, 0.0.0.0. Net mask is 0000. If I bitwise add anything with this, it will always give me this. Okay. So it matches this 124.52.0 because top 24 bits is same. Okay. But it does not match this one because top 32 bits, all of them are not the same. 7 and 114 will match. So now it matches only two of them. This still says on link. Okay, and the interface is this. So there's no difference between this. Okay. I will explain this a little later. So this is basically telling in this network. Okay. So rather than correcting to this machine, let me put it in this network. So this is basically saying this is on this network. Okay. So on link is kind of an old terminology coming from shared media, like this is on this link basically. So, but now think of that I'm sending a packet to somebody else, 172.16.10.5. Now nothing matches. Okay, this does not match, this does not match. But as I said, this will always match. Anything will match this. Okay, and this is what is called, you will see the end routes, the default route. And now you see the address is different. This is the gateway address that you put during network configuration. This is basically saying that if it does not match anything, but this matches the default route, this is the longest match you got, okay, send it to the gateway. Basically, it is saying not in this network. I don't know what to do. This is an end machine, okay. The gateway will know what to do. So just send it to the gateway. Gateway will now have a routing table to see which way to send it and so it's the router. Okay. And then 127.0.0s are this local loopback addresses. And this is, you see, this one is basically, what is this address? 10.124.52.255. All these things. This address is what? Can you tell me? 255 is all ones. So this is the broadcast address in this. So if somebody sends a message with 52 dot all ones, okay, this will match this, the longest prefix match. Again, this on network, but now your code will process this. All of these are saying it is in this network. Then there will be further processing to say what to do, and I'll do that processing exactly. Okay, but right now just remember these on links are all saying for all these cases I have found that whatever has to be done in this network. Okay, whereas if it is this one, it is a default route, which is basically saying it is not in this network, so send it to the gateway. Are you with me? Yes, no?
Yes, sir.
Okay. Ignore the metric. Okay, this metric things varies a lot between system to system, and it has different meanings. So its exact value is 35 to 91. Do not worry about it. So this is what I have said. I will just go through this quickly. So you match the destination IP for network part against routing table entries. For each entry, basically what is matching bitwise and the subnet mask to the destination IP, and see if the result is equal to the network part. If yes, you have found a match. That routing entry matches. If multiple matches, choose the longest prefix one. Then you check the gateway part of this matched entry. If it is local, on link, you'll see different things are there, or the same IP as your own machine. Then the destination IP is the same network. So there is no routing required anymore. So you need to send to that destination IP, be that this machine itself or some other machine, and so on. If some other IP, send it to the further routing, send it to. So this it is basically okay, whatever name is. It need not be the gateway only. In a router, it can be more than one. Okay. But then the question remains, and this is now we go further in. How do I send to the destination IP? Okay. So just think of this example that I have got this packet for 52.7, the one that I took. My routing table entry has said this is in this network. How do I send it to this network? That is 150. I don't. How do I know which machine is this? Okay. Similarly, to send to the gateway, I said 52.2. How do I send to the gateway? Out of all the machines on the network, how do I know which one is the gateway? Okay. So what do you think we should do? You may not be able to answer it, but I still want you to kind of think a bit. So now it has boiled down to, you are coming down to the LAN. Okay. So I have a set of machines, okay, with one gateway, okay, and here is this machine, my 10.124.52.149, and it has detected somewhere out there is a machine .7. This one is .2. It has detected this, but how does it send it? This cloud is basically a set of machines connected by switches in arbitrary topology. Any idea? You may not be able to answer it. I understand, but I just want to see, if you venture a guess. So we'll see. So how do I send to a destination machine in local network? First thing, my processing thing can directly see if the destination IP is the destination. This machine is the destination. So I can very easily check that. Now that I know it's on this network, this my machine is also on this network. So I check whether the destination matches. If it is, actually I should not use TCP UDP layer only. You will see why shortly. But send up to the higher layer protocol whose packet was there. I look at the protocol field and I see which higher layer protocol's packet is encapsulated in this IP packet and give it to that protocol side. Otherwise, forget the lower part. Okay, just focus on this. I will do this. I can do this. Okay. Now remember this. Pick the picture. So I have now IP. I have decided this is not for me, so it won't go up. So it has to go down. Go down means it will go to the Ethernet, which means I have to put an Ethernet frame header on it. And this is what I was telling. You should try to see, now that I have to send it, what values do I put in each of those frame headers fields in the Ethernet. You know what the fields are. Okay. So I can do this. In the destination MAC address in the Ethernet thing, I can put all ones, the broadcast MAC. Okay. Which means just think about how we processed an Ethernet frame. Please think with me a little bit. Okay. You can, everybody in your network will receive this. So this network is your LAN now. Okay. So everybody in the network will receive this. The Ethernet layer in everybody will look at the destination MAC address, see it is all one. That means it is for it. Everyone will accept it. Then they will look at the type field, see it is an IP, just pass it up to IP layer. So now it has reached the IP layer of every machine on my network. Now they do the same rule, okay, that we have just matched. If it is destination IP, okay, then that machine will accept it and pass it on, and the rest of the machines will drop it. The subtle thing I'm ignoring here. If you catch me, I will tell you, but right now it's not important. Okay. So the way I can reach everybody on this network is to the broadcast MAC address. So everybody's MAC layer of this network will accept it. Every machine will pass it on to the IP layer. And then the IP layer will look at the destination IP address now. IP layer will look at the IP header. Okay, I put the destination IP address is there already. Okay. And the IP header they will look at and will say whether it is for me or not. If it is for me, I will pass it up. If it is not for me, I will drop it. Right? Do you agree? This round bullet, this bullet, do you understand how I can send? Yes, no?
Yes, sir.
Okay. But then broadcasting is, a little bit less efficient. Because everybody, why should everybody pass it to the IP layer and let everybody's IP layer should run? Ideally, lowest I can, lower layer that I can drop it in, better for me. It does not go to the higher layers and kind of keep the higher layers busy. So I can also send to the destination MAC address exactly in Ethernet frame, but if no, okay, which means now in the destination MAC of the Ethernet header that I'm putting on this IP packet, when I'm resending it from the router, from my machine, okay, I will not put all ones. I will put the destination MAC address of the 10.124.52.7, the final destination machine. Okay, so that if I can do this, then at the Ethernet layer processing, only the destination machine's MAC will match with itself. Rest of the machine's MAC will not match. So all the others will drop it. 52.7 will accept it, pass it up to the IP layer. And IP layer will obviously find it acceptable, and then further processing. Okay, but the question is, how do I know 10.124.52.7's MAC address? That is where the other protocol called ARP comes in. We'll just do it shortly. It's a very simple protocol. Okay, so it's like saying, I don't know your address. Okay, so I broadcast to everyone. Okay, but I put the address in there. I give it to everybody. Okay, I don't know your name, but I give it to everybody. But then I give some higher layer name to them, the IP layer, but I don't know your MAC layer name. So whichever one's MAC, IP layer matches, they take it. As opposed to that, if I knew the MAC layer name, I could have just put your MAC layer. So everybody, you don't need to kind of pass it up to the IP layer. And what about sending to next hop? The same. It's just now, instead of sending to 10.124.50.7, the destination machine, you're now sending to your current destination next hop is 10.124.50.2. Okay. But there is a problem. We'll see. But otherwise, this thing is kind of the same. So what is ARP? ARP is address resolution protocol. It basically provides an IP to hardware address map. Okay. So basically what will happen, okay, I'll do this with an example, okay? But ARP packet, basically what will happen is, once I need to send to 10.124.52.7 and I see that I don't have the MAC address of this, I kind of pause sending this packet for a second. This packet is in limbo now. Okay, I'll send out an ARP packet which is encapsulated in Ethernet. So it works directly on top of Ethernet, kind of at the same layer as IP. Okay, and there you have Ethernet. So type field in the Ethernet will specify it's an ARP packet. I'll put it as a broadcast type. So it's kind of, I'm asking everybody, okay, what's your MAC address? This is the IP address I want, whose MAC I want, what's your MAC address? So it'll pass to the, just try to visualize, it'll pass to the MAC address of everybody, MAC layer of everybody. Ethernet will see the type field to be ARP. So gives it to the ARP software. It's a local machine. So ARP software now knows what is my IP, what is my MAC. It checks the IP. If it does not match, it does not respond anything. I've kind of said, if this is your IP, please respond back with your MAC. If this is not your IP, don't say it. So the one machine that matches, it must be, okay, that machine will send back an ARP response with the corresponding MAC in it. And again, similar to this, now I know the MAC, I'll keep it in ARP cache for some time. So next time I don't have to send these packets and wait for it. Remember, this packet is still limbo. Once I get the MAC address back, I will just do this. I'll do a complete example, but at this time, is it okay? Does it make sense? Yes, no? I'll take that as an yes. So I've just given this for reference, no need to remember. Do not try to memorize an ARP packet format or something. I'll never ask you this. But this is just for you to see basically, Miss protocol type is this one, okay? You will see source hardware address, source protocol address, its own address it will set. Its own IP, sorry, this is the IP, this is the MAC address, its own IP, own. So the other machine will also know now that this IP to this MAC map. While responding, it kind of puts one more entry in its own ARP cache. And this is the target that it wants, okay? Sorry, there's a small mistake out there. One of them, oh, it's okay. This is the target hard protocol address, and this is the one that I want to see. So this will be used in the response basically. Anyway, don't need to remember this. There's another protocol called RARP, it's opposite of ARP, reverse ARP. It gets IP address given hardware address. It's used in very specific cases, no rolling packet forwarding. I just mention it because ARP and RARP, people say ARP, then people say, what is RARP? You just need to know what it is rather than in details of it. Okay, so let's look at an example. Suppose I send an IP packet. This example is important to understand. Okay, I send it from this is my source machine. This is my destination. Okay, and this will go through this gateway. Suppose through this routing table entry mapping, I find that this network is obviously other than this, so I have to send it to this gateway. Okay, so it sends to C first. Question is, should A change the destination address to this? So this is your A, this is your B, somewhere in between is C, the gateway. Okay, so A is going, then there may be other things in between. So A is sending, it has to send to this IP address. Okay, it has a packet whose destination IP is 192.15.32.3. Okay, but now that it is sending, the immediate destination is 144.16.192.2. So what do you think? Should it change or not? Come on, I know this is hard. Online, 8 o'clock, long class. But we need to finish the syllabus, otherwise I don't prefer such long classes. Just try to guess. Make a guess, make it a little bit fun for me at least. No marks. Should I change? When I send the IP packet from A, should I replace this destination IP field with 144.16.192.2? What do you think? Anyone? Venture a guess? Anyone awake? There's no yes or no wrong answer or anything. What does your common sense say? Should I change the destination IP field when the packet goes from here to C?
No, sir.
Why not? Very good. Why not?
Because, sir, then how will C know where to say with that address?
Exactly, because see, C2B communication is like a fresh IP packet communication, as if it is generated. If you ever change this address, you have lost it. Your destination is lost. Very good. Okay. So IP address is for end-to-end communication. C will need to know that the packet is for B. Every intermediate router will need to know and do the same thing with the final destination IP. Okay. So you never change the final destination. So what do? You will look in the ARP cache to see if C's MAC address is already there or not. Okay, C is the gateway, remember. Okay, so A is the network, this is C, and then somewhere out there is B. If found, decrement TTL, if not the source, recompute checksum. So these things, as I said, kind of goes a little bit in order. So but you see, when the checksum is header, so the TTL field has changed, then the checksum changes. Okay, if the checksum has changed, sorry, the header has changed. If the header has changed, the checksum will change. So you recompute the checksum, send to the IP packet to Ethernet along with MAC address of C. So Ethernet layer will put its own header with destination MAC equal to C's MAC address and send. Okay, and now it is in the local line. All other machines Ethernet layer will reject it. C's Ethernet layer will accept it, pass it up to IP layer. Okay, and then it will look at the destination address. It finds it's not its own. Again, look at its routing table entry. The same process will repeat for the next. Okay, and if it is not found, you create an ARP packet, as I said, with target protocol address is C's IP address. Send to Ethernet with broadcast MAC. As I said, ask everybody, this is the IP whose MAC I'm looking for. Do you have it? Okay. Waits for the response, puts its own header with destination MAC equal to all one. So that's the broadcast MAC. C receives the ARP send and ARP response. Received by Ethernet, pass back to ARP processing software. Add this to ARP cache. All this time the packet was waiting. And then now you give it to the Ethernet layer. Now you have found the MAC address. So it is as if you have found it in the first place. And then you give it to the Ethernet layer and the Ethernet layer sends it to the MAC address. And C then will follow the same step. Okay. This is called IP reframe, okay, by some. So if I look at a multi-hop path, okay, so your IP will remain unchanged, okay, nothing will change, but the MAC will keep on changing at every hop, because MAC is, that's why it's a data link layer. It's a link layer. Next link, that's where its purpose ends. So next hop is my directly connected link. I put the next hop's MAC address. I use the next hop's IP address to only find its MAC address. And I know I will find it because I know that because they are directly connected, this IP and these are on a local LAN list. Is in the same network. So if I just do a broadcast MAC, it will reach the other. So I will be able to find its destination MAC. So ARP has more details I have skipped. I have just given you the basic idea. So, you know, in many implementations, if you have it in the cache, even if you are not destination, you may send it and so on. So, but this is okay. This is fine for understanding. Is it clear? There is one small subtle point that I have deliberately ignored. But again, I want you to sometime work out, sometime soon. Take just two packets, two types of examples. One example, think that a TCP packet is coming down to IP from the source. We'll go to the destination, have a couple of routers in between. Okay. So when it comes down the source, okay, you will keep on putting headers. At router, it will first go up and then come down. So go up, you will strip the headers and process them. Coming down, you will add the header fields. Okay. And then destination will go up, so you will strip the headers and process this. So just think how a packet from a TCP layer of the source goes to be. Just work with the exact header fields, see what values you will put in. When it is received, what will you do with the packet? Take an RBIT routing table, RBIT network addresses, and so on. If you work that out, you have understood the process. And this is what we wanted to do in the lab. You see, I said the packet is waiting while the ARP thing is gone. Right? Until the ARP response comes back, you cannot send the packet. All right. So you are sending a packet and you are blocked. Now think code basically. You are blocked because something must happen. This other ARP request has gone, the response has not come back. You're waiting to receive a message. But then you are not the only one sending a message through IP layer. There can be so many applications data coming in. So your net that immediately tells you that your network stack cannot be a single thread, because then everybody's send is blocked. So this is what we wanted to give you a little bit of feel of. It's not exactly done that way, but a feel of things that you must have multiple threads in the network stack. So is this part okay? So we have kind of finished the basic packet processing forwarding rules and the basic entries in a routing table and so on. Is it all right?
Yes, sir.
Okay. Good. So here are some questions for you. Okay, what happens if the user gets a wrong destination IP address? Okay, think about it. It's a very easy question. What happens when the TTL becomes 0? I've already told you. Okay, I'll check once whether the it is decremented, and then if it becomes 0, then it's dropped, or if it is decrement after 0. That's I'll just check this. But that's just a small implementation. Then what happens if the gateway next hop is dead? So you sent out an ARP request, nothing comes back. Or worse still, you have something entry in the cache, you know the destination MAC and you send it, but it does not go. So answers to these questions are easy. The second one I've already answered. What happens when the TTL becomes 0? Just think about the process and answer. Okay, so we have so far looked at the forwarding using the routing table. But then there are the routing protocols. So how the routing tables are built. Now that part we have mostly covered. So if you remember, if you know distance vector and link state protocols more or less well, the standard general description, okay, you are fine. I will just point out some simple IP network specific things briefly. So first of all, you understand, again, these are going to be very high level. So just remember a little bit of it. Okay. At the very high level, you understand that trying to make, this thing work at a scale of billions of, millions of networks, basically, in the entire internet as a flat monolithic structure is kind of impossible, impractical, impossible. So how internet routing happens is divided into what are called autonomous systems. And again, the autonomous systems have numbers. So at the networks, you still route by networks, but then your path is a collection of autonomous systems. This is a little bit complicated. Okay. But remember the term that is hierarchical. So your entire, so an autonomous system is something that is under a single administrative domain. Okay. And that may not even be a small organization. So BSNL may give 4 IPs to somebody, but then that may not get an AS number. BSNL may have the AS number. Okay. So these are kind of relatively larger organizations. Okay. So you have that. So first level is route between ASs. Okay. So routing is broken up in 2 levels, routing among ASs, which are called exterior routing protocols or exterior gateway protocols. And the most famous, the de facto standard protocol used is what is called BGP, border gateway protocol. Okay. And then routing within an ASs are what are called interior gateway protocols. And this is where the RIP distance vector OSPF link state protocol service. And BGP is the one that I have is this path vector thing that I talked about a little bit. Okay. So we will just discuss interior routing protocols now simply because of time. BGP is, even you will see OSPF is very complicated. So we'll kind of sketch these protocols. We'll do some BGP at the end if time permits. But this again, it's going to be routing tables and you exchange BGP similar to distance vector. We exchange routing tables between neighbors and so on. Only thing you don't have routing loops because you keep track of the entire path instead of just the next one. But you don't need to do that. So RIP and OSPF are the 2 things. So RIP is the older one. It's a simple implementation of distance. So almost everything about RIP we have covered. Okay, except that the destination entry, as I said, is going to be a network address. Okay. So here are some details to kind of supplement that data. So routing updates, we said periodic. How periodic it is, just to give you an idea, this is changeable, but default is around 30 seconds. Okay. And it is a destination network metric pair basically, the cost thing. RIP supports only one metric, hop count, number of hops to the destination. Also, this is interesting to know, so doesn't replace equal cost route. So suppose between 2 machines, 2 things, I have 2 3-hop paths. Okay, so A, B, okay, and let's call this X. So it has an entry. This one has an entry, destination X, next stop is B with cost 3. Okay. Now, when A advertises the route, A will also advertise the route with destination X with cost 3. So A will say X, call it C, C2. So when it comes in 2 plus 1, I will do in distance vector to 3. Okay. So there is no innate advantage in using this route. So I will not change it because it may happen so that all my traffic was going through here. Then when I change it, all my traffic will start going through here. And then this comes, okay, then I will change it again, all my traffic will go in through here. Okay, so it'll keep on oscillating, my traffic will keep on oscillating, the route will keep on oscillating if I change equal cost routes. Okay. So there is no innate advantage to that, so RIP does not do that. So in the rule that we said, when you replace, trust the next hop is fine, but then it's strict less than, not less than equal to, you don't change. Equal to, you don't change. Strict less than, you change. Similarly, when do I say route is dead? Okay, if I don't get any information for, so I don't, one thing can get lost. So I don't, if I don't get back something in 130 seconds, I don't say the route is lost. But you don't get back in multiple things, and typically that is around 180 seconds, then I say it is lost. Okay. And then I kind of delete it from my routing table, or put an infinity out there. You don't delete it immediately, I put an infinity out there. And then infinity is taken to be 60 for route. Okay. To stop that counting to infinity problem soon enough. Which means that your legitimate number of hops can be maximum of 50. Which basically means it can only be used with small networks. 15 hops sounds big, but there are many things, large organizations where 15 hops is very common. And then this is the other thing. This is where your, kind of layering and all will go topsy-turvy. So RIP is a routing protocol. Routing is the functionality of the network layer. Okay. But then if you think about how is RIP packet carried, the RIP packet will have a message format. We don't need to know that. It will actually work on top of UDP. It's kind of sitting on an application layer, and then I will put a UDP header on it, then IP header and Ethernet header and send it. Okay. And the other end will receive it at port 520. So that's all about RIP. You don't really need to know more about it. Okay? Or at least you need to know, but then everything that we have talked about in distance vector, split horizon, triggered update, Poisson reverse, counting to infinity, all those are actually part of it. Okay? Apply to it exactly as that. Only thing, as I said, destination address is network now, not arbitrary host. And these are some of the data just to give you an example of what are the parameter values that are used. What is the period? When do I change it to infinity? What is infinity? And so on. OSPF is what is very commonly used, open shortest path fast. RIP is very simple. It's not good for large networks and all, that is fine, but it's a simple protocol that does not require too much processing. OSPF on the other side is an example of link state routing. It's a much more powerful protocol than RIP. And it gives you many features. Again, I just remember a little bit. So this part you just mug a little bit. Okay, understand these 1-2 lines. They're easy to understand, but we'll not do any details of OSPF and all. It's not. There are books on OSPF. It's quite complicated. But load balancing, so it allows you to keep multiple routes with the same cost, unless the RIP thing. So in this earlier example, you can actually keep, if this is 2 pass with hop count 2, this can keep both these routes here. So you can enable these things, all these things. And if there are multiple routes, then the traffic to this from here, okay, can be equally distributed over this. So kind of load balance the thing over multiple routes. So the routing table will have 2 entries with the same cost. And you can enable a feature in OSPF so that traffic for the end destination, part of the traffic, first IP packet will go there in kind of a round robin fashion. Okay. It can handle type of service. So you can install multiple routes. You can say low delay, send it through this route. The routing table now entry can have multiple entries and say low delay, send it to this route. You want high throughput, send it to this route. Okay. So your routing table matches will not just be on the network, but also on the type of service. It's a more secure protocol. The routing tables, routers actually are very sensitive points of attack, because if you can change the routing table, you can direct packets towards yourself. To one of your own routers, okay, where you can just filter it out and know what is going on in the packets and so on. At least you got a lot of packets. Okay. Or in the very least, you can disturb the internet. So routers have, in general, routers as system have strong authentication, but when you exchange these messages, just to kind of support that a spurious router, any kind of a malicious router is not sending you wrong routing updates and so on, you can have authentication basically. And this is a big thing that is used, supports hierarchical routing. The large organizations can also be very large. Okay. And if you have like thousands of machines in an organization, again, having all these 1,000 doing link state. Okay. So you have a very large organization with lots of machines out there. Remember, link state is what? You will know the entire topology and then do dice class, basically. But with a very large network, taking the entire topology is a lot of time. Okay. So you can allow you to kind of break this up into small areas and then have this not hierarchical really, sort of. You have, I will not go into details. You have area border area routers, basically area border routers, which can now communicate. So this topology is written from this network. So nobody here knows about the topology here. They only know the topology here, and some aspect of the routes come here into this one and so on. Okay. So you don't need to kind of know big ones, but basically remember that you can break up into smaller self-contained areas. Okay. It supports the use of different cost metrics, works directly on IP. Okay, so less overhead, you don't have the UDP overhead processing and so on, less errors and so on. I'll just put a few slides just to give you an idea. Okay. Again, just remember the sketches. So each node will mention a database of link state advertisement. Okay, so how is this topology? Everyone has to know the topology. What is this topology? So it's a collection of LSs, and LSA contains information about a link, actually about two nodes on the link basically. So it'll have some information about this originating router and the end router. Okay, but that's kind of. Then you have an age field in each entry to keep track how long that LS is not updated. If somebody tells you, okay, that this is the link, and then does not tell you anything for more than 1 hour, 2 hours, you do not know, because he's working on top of IP, whether nothing has changed or something has changed that other link routers has told you, but the packet got lost because it's an IP packet after all. Okay, so you keep an age field, kind of a routing cache time limit, kind of saying that, okay, up to this I will believe this is the correct information. If the age is exceeded, typically around 1 hour, okay, then I will assume something may be wrong. I may request this thing for something else, again, basically. So you remove it, if not within some time, okay, and then sequence number because you're flooding, okay, then maybe one old packet was on this path, so it will reach here much or later. But then lots of this link has changed, the cost on this link has changed or something, and this new packet has already reached. So when this old packet reaches, the standard problem is flooding. Okay, how do I know that's an obsolete packet? So like every time a node sends out an LSA about a particular link, it will update a sequence number. So if I have its current sequence number is 130, I get a LSA with 120 sequence number, I will assume that it is an old one, I will not update. Okay. These are standard techniques. Age and sequence numbers are standard techniques for keeping track of the current or obsolete things over there. So when two neighbors discover each other for the first time, they exchange their LSAs. You say, what information about topology do you have? Give me all your LSAs. And there are some messages from them. Okay. And there may be lots of LSAs, so you can send multiple messages. So kind of you and I discovered each other for the first time. We are kind of exchanging information about what do I know about the topology? What do you know about the topology? Okay, and topology is nothing but a set of links which are basically the LSAs. Okay, and the LSAs actually have the originating router and the end router and some other information out there. And then LSAs will also be flooded periodically, typically, but not much later, typically 30 minutes as compared to the 30 seconds flooding. But this is flooding, so it is reaching everybody. Everybody will flood, get it, process it, flood the next year its own LSAs basically. Okay. So it's around 30 minutes. And LS is a checksum for error detection, acknowledged for reliability. Okay, but acknowledgement is only end-to-end, as you know, that notes things may happen also for things to get dropped. And I've just noted some messages. So this hello message is what keeps you alive. The hello message is a very standard message in so many protocols. How do you know your neighbor is alive? Either you ask it and it responds, or it periodically lets you know. So I'm going through this pretty fast. You can just read it later on. Okay. Just to give you an idea of difference. So link state request sent to a neighbor to ask for status of some specified links. As I said, I have an age field has become too high. I've dropped a link. I may request into saying, what is the status of that link? Do you know the status of that link? Link state updates are the ones that are sent periodically or detecting a link change. Each of them contain a number of LS entries. Link state acknowledgement is the acknowledgement. And DBD are this initial exchange when I said, give me your database, give me all the LSs that you have. Okay. Works directly on IP, protocol value 89. All OSPF messages sent with TTL equal to 1 in IP header. So they will just reach the next one. The next one will send again, but then that's it. It's all supposed to mean to reach only one. The flooding happens because everybody sends with one of that. It's a powerful protocol, but then more details will not go into at all. So to summarize, RIP, you have covered in detail. So everything that we have covered in distance vector in detail, everything applies to RIP directly. Okay. Including the split horizon, triggered update, poison reverse. There's something called hold down that we have not covered, but that's okay. So the RIP part, that was a couple of slides I had just to give you an idea about some of the parameter values, this UDP uses and so on and so forth. Little bit of detail that you should remember. Okay. Whereas OSPF is basically a link state protocol. Okay. But it's a much more powerful protocol rather than just sending the link state updates and building the topology running dice. That's what it does. Okay. It keeps the topology as the 6 cents, as a set of LSs, the link state advertisement messages. It exchanges LSs, kind of floods LSs when something changes, or periodically the entire all the LSs. Okay. It stores the LSs, the age and sequence number, and once it is the topology, it runs disters to do this. But beyond this basic principle of link state routing, okay, OSPF has a lot more details and so on. So the messages that I have said in the basic operation, just try to link it with the basics of link state routing that you have covered so far. Okay. But then remember that LSN or OSPF can do a lot more things. Like some of them I have mentioned, and there's a lot more complexity. The exact message formats are not important for any of these protocols, either RIP or OSPF. Okay, so we have kind of covered one major part of IP, which is routing and forwarding. We have seen what an IP header is, basic IP address, notions of IP address, classful, classless, subnetting, supernetting, okay. Routing table, building the routing table with distance vector link state, with a little bit of details about the actual protocols, okay. The routing architecture, that hierarchical architecture, even though we have just kind of specified, okay, just remember that much. AS, BGP, exterior, interior, remember the names. Okay. And we have gone in details, and this I'm again telling you, please go through this, it will be useful for your exams, okay, and for your understanding. Exams is not the main thing, to me at least, is how a packet is processed at the IP layer. How does a packet, in an end machine, which is a source and destination, or in a router in the middle. Okay. So that kind of completes one part of your IP. I'll end with a little bit of couple of slides on the practical aspects of funneling. So this kind of going to be the basic structure of a router. So these parts will be mostly, so you will have a processor inside. It's just not your general purpose processor. It's a very specific processor. Sometimes there's an ASIC inside, application specific IC. You'll have a memory and everything. Okay. And then you will have these input ports through which your data will come. Typically, again, high-end routers, each ports will have one separate input. This will have some processing. Remember, what is coming in is signals. Okay, you're connecting this. So when it goes out, it actually goes out at the physical layer. So all your physical layer processing, okay, all those things that you're talking about, your frame processing, everything is happening here. Okay, it's just that when the switching fabric is coming in, it is actually, it's looking at the IP address, the layer 3 address. That's why it's a router or L3 switch. But doesn't mean, just try to visualize a bit. Okay, you will connect this. This actually signals going out to this port, and this will connect to another router signals this port. So these are like standard encodings, encoded signals that we have seen. So this has to do the encoding when it sends out. Then the processing has to be done for the Ethernet and so on. Finding the frame, checking for CRC, all those things are happening in this logic out here, basically. Again, this kind of a high-level picture, but then it's buffered, and then the routing processor basically picks it up from the buffer, looks up this routing table and everything, and decides, so this input port should go to here. So it kind of sends it to, kind of puts it out here, and so on and so forth. It's a very standard picture in different forms, but this is kind of what it is. What is important to understand is that two things I want you to know, that we talk about routers, IP, etc., but this box that is there, okay, does everything basically, because what is finally coming in is the signal, the encoded signal that you have. So the PHY processing will happen, physical layer processing, Ethernet framing will happen, and so on. It will be passed all the way to the IP layer. Remember the router picture I said, physical, Ethernet, IP. And then the decisions will be made at the IP layer, the routing table and everything. But then it will be passed again through Ethernet. So I will do the Ethernet processing of putting the Ethernet frame header, go to the physical. So based on the Ethernet type used, you'll do encoding, etc., and send it out. So it's not just IP processing, it's all the processing in a standard router. And typically the ports will have buffers. Okay. So they will be buffered, picked up by a processor according to some policy. Okay. Looked up the routing table and so on, and then sent to the corresponding output port. And this is where the packet drops come, because if this is coming in too fast, faster than the routing processor can take it from here, process here and send it out here, then these buffers will kind of fill up here. And then you can have a packet drop because there is no more space, as simple as that. So typically high-end switch routers will have a lot more buffer space. So this memory in the router is one thing that determines its cost. One major primary thing that we look for when we purchase a router and switch. And the other practical thing is talk about L3 switch. You hear this, you will hear this term a lot. Okay. So old days, router was router. There was an Ethernet switch and then router. But now we have L2 switch, Ethernet and L2 switch are synonymous. You have L3 switch. L3 because it is switching based on L3 information, which is the IP address, layer 3 from bottom. Okay. So all the functionalities that we have studied, and there is one more that's okay, that can be done by an L3 switch. So the difference between a router and a good L3 switch is kind of confusion. Again, if you look at this is the bridge versus router kind of thing. Even though, as I said, bridge and router, I can point out some very specific things. Okay, you'll see a lot of debate out there. Most functionality is the same. The basic functionality is the same. However, general. Okay, and this is kind of again which router, who is using terminology, and so on. A router will generally have more features, more policies, more configuration settings, and so on. Can connect to a wider variety of WAN technologies. So this is what I was saying. Okay, so this one port of a switch goes to the other port. I said just to do the physical layer processing, Ethernet processing, and so on. So when you look for the interfaces, you'll say Ethernet, 10G interface. Okay, so it's basically a 10G Ethernet interface. So if you look at the ports of an L3 switch, typically there will be 1G, 10G, 25G, 40G, 100G Ethernet ports. Okay. Whereas routers have the ability to actually connect to, you can buy a router with more number of types of port space. Even though Ethernet is kind of becoming the de facto standard, so now that definition is also kind of getting blurred. Typically have lower number of ports because its primary purpose is to route between networks, not connect smaller networks. Okay, and it costs more. But these are, once again, I emphasize, okay, like this is what is kind of the street knowledge about routers versus L3 switches. But basic functionality wise, okay, both are the same. So I can make my IIT Kharagpur network completely work without a router also with an L3 switch. We have a router right now, but the functionalities are same. As I said, routers have a lot of policies, configuration features, and so on. Cost more, gives you more features, as simple as that. But then you may not need all of them. So it's kind of blurred. Okay. So purpose of basic routing and forwarding that we have studied so far, both of them are fine. But if somebody kind of asks you, what is a router and L3 switch? I think the summary answer is that it is kind of the same with respect to basic routing and functionalities, but this however points is the points that you can kind of say that sometimes routers will have this. But I just wanted to point out because L3 switch is a common terminology. Finally, today I want to show you how will the switches look like. So it can look like this in the top. As you see, oops, sorry. And as you see, this looks like a normal. This is a 48 port L3 switch. Okay. This is standard Ethernet ports and so on. Right? Or higher end things can look like they're called chassis based things. What is chassis? So this is like a monolithic structure. You get this box and you put it. Okay. Whereas a chassis based switch is something like this. Okay. So you have a chassis and then you kind of put in cards in there. So you buy the chassis, you only buy what is needed. So these are your kind of control cards. These top two things, top four things that you see. It's called line cards, control cards, and so on. And these are the actual ports. So today I need 48 ports, something, I buy one card. Tomorrow I need something more, I can just buy another card and put it in. As opposed to buying the complete control logic again and increasing the cost. So initial upfront cost is higher. Okay, and chassis-based switch is meant for back-end, high-end things basically, not just so typically your hostels do not get connected to chassis-based switch directly. Your hostel gets connected to aggregation switches like this. Okay, and then many of these aggregation switches will get connected in the back-end, so they will need higher capacity and so on. Okay, and as I build hostels, build more departments, I will need to increase the capacity. So when I build a new hostel, I'll put an aggregation switch, connect all your wing switches to this, and then take one wire out from here and connect to the core switch in CIs. And if I have increased my capacity over there, say run short of ports in the core switch, I'll buy one more card and put it in there. This is what is called a chassis-based switch. Are you with me? Yes, no?
Yes,
Yes.
sir.
Okay. So network is, I'll stop here today, but don't leave yet. So there's some other part fragmentation would have been good to start today, but it's okay. I think I don't want to start at 9:30 today. You're already a long class. So we'll take one more class to finish those two basically. So networks, as I said, means it's hard. Textbooks are very important. Okay. And what I'm teaching you now, the IP part, you will find everything in Command. Okay, we'll find a lot more out there. Okay, but there are things that that will be there the way it is taught. It's not there in the textbook basically. So, but you need to, as I said, in the systems thing, you need to kind of practice how are things working. At least ask yourself a question. And that packet processing thing that I said is extremely important. Otherwise, you will have seen IP thing. Ethernet thing, separately ARP thing, you'll all know it, but you will not be able to integrate this. So let me kind of jolt your curiosity a little bit. See these ports, okay? Now, how all these things, what you have learned basically should make you think. Okay, when you think about, think about both things. At the bottom level, think about the devices that will be there. We'll show you some of them, okay? But you can always see pictures if you're curious in the code. And think about how are you going to physically connect them with wires? What will get plugged in where? To get a feel of the physical thing. And then think about the software that is running on this, and think about the packet processing and all those things, which integrates all the protocols working. So let me go back to the physical thing. You see these small holes, these ports out there. Okay. Now these ports, the shape of the ports reminds you of something. Just think of one of these small holes out there. Let's say here, one of the small holes.
So it's an RJ45.
Okay, very good. Okay, so shape is kind of an RJ45, right? Now, Western knowledge, RJ45 is used for what kind of cables?
The UTP.
UTP cables, right? For certain amounts, some of the that's T lines basically. 100 base T, 100 base T, 1000 base T, and so on. So the copper cables. Okay. So will the switch completely change if I have to connect a copper cable or I have to connect a fiber? So tomorrow, okay, today I have less bandwidth requirement. So on one of these ports, I have connected a copper RJ45 cable. Okay. Tomorrow, the load on that, wherever this wire is coming from, has increased, the indication switch. Okay. I want to and I kind of want to extend its length, for whatever reason. I want to connect a fiber out there. Should I have to throw out the line card and buy a new line card? This line card means this card out there. What do you think? These are not for the exams. Okay, but you know about networks, what is happening around you if you ask questions like this. So what do you think? Just try. We'll not teach you anything new.
So we probably need an adapter.
Very good. Okay. So you should not, because your basic processing is the same. You will have the same routing processing. The only thing that is changing between the UTP and the PHY is basically the physical layer details, UTP and the fiber, and the connected type, and so on and so forth. Okay. So when you buy these port line cards, okay, you will see there's a hole in there, not this nice RJ45 looking holes necessarily. Okay. And remember, for optical fiber, it's even strange because see, in the physical layer processing, electrical is electrical signals. Optical fiber, somebody has to transform that, optical to light to electricity or electricity to light for receiving and sending. So the physical layer processing will be completely different. Okay. So that's the question. When you try to think about plugging this thing, you need to, and then you look at the cost and all, then the people cannot be that stupid that you have to throw out a line card just because you want to connect a fiber instead of a copper. Okay. So lower cost switches will have fixed things sometimes. Okay, sometimes, but even there, the higher end L3 switches are still quite costly. So you will have an adapter. These adapters are called modules. So when you buy this, the ports will actually have holes in there, and you will I would, if the class happens in offline, I'll come and show you basically. I'll pass an adapter, the fiber adapter, for example, in class from CIC. You kind of put that adapter, you plug that in. The modules you have to buy. Why is this important? Okay, again, from your research and all, not a great deal. You need to know physical layer and all. But when you have to plan your network, you have to buy equipment and all. Okay, lots of time you buy a switch and the wrong type of adapter, and then your switch is useless. And adapters are sometimes costly. Depends on who you buy it from, what type of adapters and so on. So all I'm trying to point out, is it important to know this information? So depends. To me, everything is interesting. Okay, but all I'm trying to point out is that if you try to kind of think about where will I plug this where, you get to kind of ask yourself and then kind of bring in your knowledge from physical lab to everything. You have to see. Otherwise, there are so many times I have asked 4th years, 5th years in Vivas and so on about what happens in the router. Okay, and there's IP, routing table, everything, and then they say, okay, but then where is the Ethernet thing happening? You would not believe it, the number of times I get this answer. So before the port, I have to put another device. And if you go out and say it to the world after an IIT Kharagpur degree, okay, then you should be ashamed and we should be ashamed as your teachers. Okay. But then it's, as I just pointed, it's very common sense. You just think that that has to happen inside the switch. Okay. So just ask yourself these questions and always do end-to-end things. Will tie these protocols together. When you do TCP UDP, again think of a TCP packet going in, all the things you learned in the lab. Okay, just think. So if I make a connect call, what is happening? What basically packets are going. Just think what packets, what headers, what will happen. Okay, so enough GAN for one day. So we'll stop here and we'll come back next Monday. So tomorrow I'll go to Nalanda and see what instructions they have, because the date is 10th. So if they are willing, they will be available and all. Then I'll talk to the dean to see if we can start something on 7th. But again, there's few students in the class to actually discuss this. Let me just stop the recording anyway. Right? Just give me 1 sec. So we have 18 people in the class.